So I'd like to talk to you a little bit about some very recent work, as yet unpublished, that I've been doing along with my collaborators, Chris Godsell at the University of Waterloo, Robert Chamal at Charles University, Dave Robertson and Antonios Varvatsiotis, who are both kind of at the National University of Singapore and Nanyang Technological Institute. So the project I'd like to talk about involves looking at homomorphisms on graphs and how we can use colorings, and specifically vector colorings, to gain some information about kind of homomorphisms between graphs, and most kind of pressingly or intriguingly about kind of answering the problem, when is a given graph a core? So I'll start by kind of defining all of my terms, or some of my terms at least. So for those of you who aren't familiar, so homomorphism between two graphs, G and H, is simply a map between their vertices. So I'm mapping my vertices of my graph G to the vertices of my graph H. And I require that my map preserves edges. So if I have an edge in my graph G, it's always mapped to an edge in my graph H. And I don't really care about what happens to non-edges. So for example, some simple examples of homomorphisms. If I have two graphs that are isomorphic, then obviously any isomorphism between them is a homomorphism. I have any automorphism is going to give me a homomorphism from the graph G to itself. If I have some graph G that's a subgraph of H, then any embedding is going to give me a homomorphism. And then non-trivially, I can also construct homomorphisms as follows. So this 3 coloring of the 5 cycle gives me a homomorphism from C5 to C3, or K3. So homomorphisms are kind of natural things to look at. They kind of give you a description of the structure of your graph in some way. And now once we have this, this class of morphisms between our graphs, we can look at the order they induce. So I'll kind of think of G being sort of related to H if I have a homomorphism from G to H. And this order is in some ways well behaved. It's reflexive, so we've already seen that G is always related to itself. It's transitive. So if I have a homomorphism from G to H and a homomorphism from H to K, then just by composing those homomorphisms, I'm going to get a homomorphism from G to K. This is easy to see because my map from G to H preserves edges, and my map from H to K preserves edges. So my map from G to K is also going to preserve edges. But unfortunately, this order is not anti-symmetric. So here's an example. I have, say, a complete graph. I can embed this complete graph in a complete graph with some pendant edge. And I can also construct a homomorphism going the other way. So these two graphs are going to be homomorphically equivalent, but they're not the same. So this means that my homomorphism order fails to be a partial order, which is kind of unfortunate. So in that way, kind of the homomorphism order on its own is a little bit of a hairy thing to get a hold of. But we can make some sort of a simplification. And the way we do that, or one way that we can do that, is as follows. So I can define an equivalence class on graphs, an equivalence relation on graphs by kind of defining G and H to be homomorphically equivalent if I have a homomorphism from G to H and from H back to G. So those two graphs that I just helpfully erased are homomorphically equivalent to each other. So this breaks my class of all graphs into these homomorphism equivalence classes. And I'm going to define a core is a graph G for which there's no homomorphism from G to any proper subgraph of G. So another way of saying this is that all the endomorphisms of my graph are automorphisms. And it's a long-standing, well-known fact that every graph contains a core, contains cores. You can just keep look at your large graph G and keep finding homomorphisms to smaller and smaller subgraphs. Eventually this process stops. When it stops, you've reached a core. And the core of a graph is in fact unique up to isomorphism, of course. You may find several copies of the core of a graph inside, but they're all going to be the same core. So this tells us that cores form the unique minimal representatives of the of this equivalence relation, the equivalence classes of this equivalence relation that I've defined here.
So is it easy to see that why it's unique?
No, I mean it takes some work, but I mean it takes a little bit more work than I have to have time to go through right now. This is a fairly standard result, though. It's not hard to find proofs of that. I mean, any kind of textbook that handles basic homomorphism, graph homomorphisms will have that result for sure. Right, so these our cores are these unique minimal representatives. And if we restrict our homomorphism order to the class of cores instead of the class of graphs, everything becomes quite nice again. Now we get a nice poset that has better structure than the general homomorphism order. So these are reasons why we might be interested in studying cores and in answering kind of the obvious question. If I give you some graph, can you tell me whether or not that graph is a core? And this is not an easy question to answer. But so for the rest of the talk, I'm going to be talking about a tool that kind of myself and my co-authors have developed that can answer this question in some small cases. But before we get there, I'd like to talk a little bit about colorings. So we saw that we were looking at homomorphisms. I drew the example that a 3 coloring of the 5 cycle gives us a homomorphism from C5 to K3. And kind of quite often, if you want to introduce or start talking about homomorphisms, I would maybe have inverted the topics in my talk. Maybe I would have started talking about colorings and then showed you how homomorphisms are sort of a generalization of colorings in some sense. But kind of we'll get there now. So if G can be colored with C colors, then there exists a homomorphism from G to the complete graph on C vertices, and we can define the chromatic number as the minimum, the size of a complete graph for which G admits a homomorphism to K sub C. So it's not very hard to see that that this is sort of a perfectly workable definition of coloring, and sort of is exactly the notion that we're all very familiar with. And so if you like, you can think about constructing a homomorphism from G to H as finding some H coloring of the graph that you started with, of the graph G that you begin with. So now if you recall, we saw that the homomorphism order was transitive. That means if I find a homomorphism from G to some graph H, and I know that H is C colorable, then I know my graph G is C colorable. So this means that chromatic number is what we call a homomorphism monotone parameter. So i.e. if I have a homomorphism from G to H, I immediately know that the chromatic number of G is bounded above by the chromatic number of H. And this immediately allows us to rule out the possibility of homomorphisms between two graphs we might be interested in. So for instance, so immediately, given this fact, we can show that the graph C sub k is a core if and only if k is odd. So if I have an even cycle, even cycles are bipartite, so I can two-color them, so I have a homomorphism to K2, and of course I can embed K2, the edge, in any graph, well, any graph with an edge. C2k definitely has an edge. So C2k is not a core. Now if we look at C2k plus 1, I definitely don't have a homomorphism to K2 because odd cycles are not two-colorable. And in fact, I don't have a homomorphism to any proper subgraph of C2k plus 1 because any proper subgraph of C2k plus 1 is bipartite. So this implies immediately that this graph is a core. So this is a very simple example of a very common strategy when it comes to proving kind of the non-existence of homomorphisms or that graphs are cores. You find some parameter of your graph that's homomorphism monotone, and then you use that to show that your desired homomorphism can't exist. So coloring is one way, kind of one example of this. So another example is using, instead of the normal chromatic number, we can use the fractional chromatic number. So I'm not actually going to give you the standard kind of proper definition of fractional chromatic number. So where fractional chromatic number comes from is you can phrase or you can express the chromatic number of a given graph G as the solution to an integer program. And now once you have an integer program, the natural thing to do is to relax it to a linear program. And if you do that, you wind up with, so solutions to that, the optimal solution to that linear program is called the fractional chromatic number of your graph. So that's not a definition, but I'll call this chi sub f of g. And you can show that chi sub f of g can be defined, just as we kind of looked at an equivalent definition of coloring in terms of homomorphisms, we can define chi sub f in terms of homomorphisms. So this fractional chromatic number is the minimum of n on k, so that G admits a homomorphism to the Kneser graph k sub nk. So this Kneser graph has vertex set all k subsets of the numbers 1 through n, or any n set that you like, and two k subsets are adjacent if and only if their intersection is disjoint. So for example, coming back to the 5 cycle, you can embed the 5 cycle, obviously, in the Peterson graph. So here I have a homomorphism from C5 to the Kneser graph K sub 5, 2, otherwise known as the Peterson graph. And this isn't a proof, but it's not difficult to show that, in fact, 5 on 2 is the fractional chromatic number of the 5 cycle. And again, because I have this parameter defined in terms of homomorphisms, if I have a homomorphism from G to H, and I have the normal upper bound on chromatic number. So now I can start computing fractional chromatic numbers, and using that parameter to rule out homomorphisms. So most notably, this is done as follows. Just as for chromatic number, we have a trivial lower bound on the fractional chromatic number, just the number of vertices of my graph, divided by the size of a largest independent set. And if G is vertex transitive, so a graph is vertex transitive if there exists for any pair of vertices u and v, an automorphism of my graph that sends u to v. If my graph is vertex transitive, then the fractional chromatic number is equal to this value. So there's a class of graphs, vertex transitive graphs, for which this parameter is very easy to compute. Well, provided you know the independence number, which is not easy to compute. But,
Usually you can compute the fractional chromatic number easier than the...
Yes, yeah. So yeah, compute's the wrong word. You know the fractional chromatic number is what I should have said. So from this theorem we have, as a corollary, a very famous theorem. This is known as the no homomorphism lemma. First shown by Albertson and Collins in 1985. And it says that if I have a homomorphism from G to H, and H is vertex transitive, then I have the following inequality relating the what's often called the independence ratios of these two graphs. So the size of the vertex set of G divided by the size of its largest independent set is at most the number of vertices of H divided by the size of its largest independent set. And again, this is typically employed as a tool to show that, not to show that given a graph G with a homomorphism to H, I have this nice relation, but instead to show that because this relation is broken, I can't have a homomorphism from G to my graph H that I'm interested in. All right, so one more. One more variant of chromatic number. So the vector chromatic number is defined in the following way. Well, I'll give you the idea first. The idea is I have the vertices of my graph, and I want to map them. I want to construct a map from the vertices of my graph to the vectors, or to some vectors in Rm, where M we'll kind of leave for now. M is sort of weirdly unimportant. I just have some space R to the M, and I'm mapping my vertices to vectors. And I require that not only do I map to vectors, I map to unit vectors, so I'm mapping my vertices to elements of the unit sphere in this Rm. And I want vertices that are adjacent to be mapped to vectors that are kind of far apart, or points on the sphere that are far apart. So formally, so this is my condition. So for some t greater than or equal to 2, a vector t coloring of a graph G is going to be an assignment of my vertices to unit vectors in Rm, so that whenever I look at adjacent vertices, the inner products of the vectors that I've assigned to those vertices is at most negative 1 on t minus 1. Seem to be out of 1 there. It's just hiding. So so in actual fact, for the majority of this talk, I'm going to focus on strict vector coloring. So now not only do I want a vector t coloring, so not only do I want this inequality, but in fact I want to have equality for all of the edges. So I want all of the edges, all of the endpoints of edges to be equidistant.
Excuse me, why does shift starting t with 2 but subtracting?
So why not define, so for t greater than or equal to 1 or something like that? That's a good question. So I don't have a convincing answer, is the answer. So these vector colorings were invented relatively recently, in the last decade or so. So where they come from is, so in a moment I'll kind of define what the vector chromatic number and vector strict chromatic number are, and you can express those parameters in terms of a semi-definite optimization program. And I imagine that's some sort of an artifact of that construction. I don't really know. Sorry about that.
This construction, what is m? Is it
Right.
the number of edges? Or?
No. So as I said, m is just some parameter that works.
Oh,
M is just sort of, it looks very strange because it sort of looks like optimization problems where you're taking some space r to the m, and then you're looking for things like maximum sets of equiangular lines or something like that, and you're wanting to pack as many of these points at constant distance from each other onto some given unit sphere. But that's really not what we're doing. We're just looking for some space that works. So all we're interested in doing is minimizing t. So m is kind of incidental. So let's see an example. So going back to our favorite example by now. So in R2, if I look at the unit spherical and I take the points that are going to correspond to the fifth roots of unity, I get a strict vector root 5 coloring of the 5 cycle. And in fact, this is again optimal. So for strict vector coloring, this is actually a different parameter in disguise. So it turns out that actually I didn't define what those chromatic numbers were. Hold on a second. So the vector chromatic number and the strict vector chromatic number are defined in exactly the way that you'd expect. So the vector chromatic number is simply the minimum t, such that G has a t vector coloring, and the strict vector chromatic number is defined in the same way, except now I'm looking at strict vector t colorings and not simply vector t colorings. So if G is any graph, then it turns out that the strict vector chromatic number of G is equal to the Lovash theta of the complement of G. So if that means something to you, then there you are.
That's why you subtract 1.
Ah, okay. Possibly, yeah. So I should do at least something to convince you that these parameters are sensible in some way. So here's another example. So if you map the vertices of the complete graph on n vertices to the vertices of the n-1 simplex in R to the n-1, what you get is a strict vector n coloring of the complete graph. And in fact, this is optimal. And so this shows that again, because I can, my homomorphism relation is transitive, I must have that the strict vector chromatic number of any graph G is no larger than its chromatic number, and it can be no less than its clique number. So this omega of G is just the size of a largest clique that's contained in my graph G. And of course, again, these are examples of homomorphism monotone parameters. So we can play the same game that we've been playing so far. We can look to rule out homomorphisms from G to H by computing their vector chromatic number or their strict vector chromatic number. But what we're going to do, is something different. We're actually not going to look at the vector chromatic number. We're not going to be so concerned with the chromatic number itself. We're instead going to work with the colorings that we get, these maps into our Euclidean spaces. So just as we had this nice class of graphs, vertex transitive graphs for the fractional chromatic number, where we kind of knew the answer already, we can also find a class of graphs for which it's very easy to find a canonical optimal strict vector chromatic strict vector chromatic number valued coloring. And the graphs we're going to look at are called one-walk regular graphs. So what is a one-walk regular graph? So a graph G with adjacency matrix A is said to be one-walk regular if, for all natural numbers k, there exists some integers a sub k and b sub k, so that if you take the adjacency matrix of your graph, raise it to the kth power, and then take the Schur product with I, so this fancy circle here is the Schur product, or just the entry-wise product. My supervisor was fond of calling this the undergraduate's product. It's the way you want to take products of matrices. So if you take the Schur product of a to the k with the identity matrix, you get some multiple of the identity matrix. And if you take the Schur product of a to the k with a, you again get some multiple of a. So what does this mean combinatorially? So these two conditions are exactly the same as So the first condition is just that the number of closed walks that begin at some vertex u of my graph and have length k is independent of the vertex I start at. And the second condition is kind of the same thing except for an edge. So the number of closed walks on an edge uv of length k is independent of the edge uv. So if you want some examples of graphs that are one-walk regular, sort of the most obvious example is distance regular graphs. Or if you've not seen distance regular graphs before, then you've probably seen strongly regular graphs, which are just distance regular graphs of diameter 2. So strongly regular graphs are one-walk regular, and kind of slightly more broadly than distance regular graphs. Any graph that corresponds to a single class in an association scheme is going to be one-walk regular. So these are graphs with some fairly strong algebraic structure to them. And because of that structure, we can construct vector colorings in a fairly natural way. So let's go ahead and construct these vector colorings. So all I'm going to do is I'm going to take some scaling of a fairly standard object, the representation of the graph on its least eigenspace. So what is a representation on an eigenspace? If I have a graph G, and I let theta be some eigenvalue of my graph, what I'm going to do is I'm going to let P be a n by, so the number of vertices of my graph are going to be the number of rows, and the number of columns are going to be the multiplicity of my eigenvalue. And I'm going to construct P by taking any orthonormal basis for the theta eigenspace and just slapping that in as my columns. And once I have my matrix capital P, all I'm going to do is I'm going to map each vertex to the vector in R to the m sub theta corresponding to the row, the vth row of that matrix P. So for a vertex of my graph, I'm going to let P sub v be the vth row of P. So either the map or the set of vectors corresponding to the rows of this matrix are a representation of G on its theta eigenspace. So these pop up here and there in the literature. Sometimes they're referred to as representations on an eigenspace. Sometimes they're referred to as Euclidean representations. Using these representations, you can simply by looking at the convex hull of the vectors that you get, you construct what are called the eigenpolytopes of the graph. And this is almost what we need for a vector coloring. So for a one-walk regular graph, for a one-walk regular graph, these vertices are all going to have constant length, but they won't be a unit length. So all we need to do to construct a vector coloring from this set of vectors is to scale, so I normalize everything. So this is a theorem of Chris's. It says G is a one-walk regular graph and with least eigenvalue tau, and P is constructed as before. Then the map, where I simply map V to the root of the root of m on tau times this vector P sub V is a is not only a vector coloring of my graph, it's a vector coloring of my graph with optimal value. And in this case, when we're looking at a one-walk regular graph, we have that the strict vector chromatic number and the vector chromatic number are the same. So that's not true in general, but it will be for the specific class of graphs that we're looking at. So one thing to note about this construction, or about these colorings, that's sort of quite a bit different than either colorings or fractional colorings, and that is for many graphs, and for kind of particularly the graphs that we're going to be interested in, the graphs that we're going to prove are cores, this map is injective. So I'm not mapping any vertices together. I'm actually getting an embedding of my graph, in a sense, in the unit sphere, which is kind of slightly strange if we're thinking about this as a coloring. So this map is injective for the graphs we consider. Which graphs are we going to end up considering? Well, more or less distance regular graphs that are non-bipartite. So if we're talking about homomorphisms and we're talking about cores, bipartite graphs, as we've seen, are not interesting. Bipartite graphs have a single edge as their core. So an example. The root 5 vector coloring of C5 that I showed you, where you just map every vertex to a fifth root of unity in R2, is constructed in exactly this way. That picture is a representation of C5 on its least eigenspace. Okay, so how can we use this to say something about homomorphisms? Well, before we can, I need kind of one more notion. So I'm going to call a graph UVC, which stands for uniquely vector colorable, if all of its unique, so optimal vector colorings are the same. Of course, I don't mean actually the same. I just mean that you can either the Gram matrices of two distinct optimal vector colorings are the same, or equivalently, you can get one optimal vector coloring from another by an orthogonal transformation of Rm. one of the theorems that we've kind of come up with as a part of this project is a criterion for when a one-walk regular graph is going to be uniquely vector colorable, and this is the condition that we wind up with. If G is one-walk regular, then G is uniquely vector colorable if and only if it satisfies this kind of unwieldy looking condition. So our graph is one-walk regular. I know what the optimal vector coloring, the strict vector chromatic number is. I have an example of an optimal vector coloring. That canonical example of an optimal vector coloring is unique if and only if it satisfies this condition. And this condition just says that if I look over all m tau by m tau symmetric matrices R, if this product is 0 whenever I'm looking at vectors of my representation that are either the same vector or correspond to adjacent vertices, then the only possibility is that this matrix is the 0 matrix.
This is a property of the coloring, right?
Yes. Yep.
I think PU is...
Yes, so this is the... Yeah, sorry if I didn't make that clear. So this is, that canonical vector color. But of course, you can take any one you like. You can take any rotation or orthogonal transformation, and it will satisfy the same property. So this condition kind of is related to something called the Strong-Arnold condition, or Strong-Arnold hypothesis. So if you're familiar with, say, the Collin de Verdière invariant for graphs and its related parameters, this kind of a thing pops up there as well. Anyway, so this is a condition, and now we can use it to show that graphs are cores. So how do I plan to do that? Let's go back to cores for a moment. So I'm going to let n sub u of g simply be the neighborhood of the vertex u in my graph G, the set of all vertices that are adjacent to u. So homomorphism is called locally injective if it is injective on all neighborhoods of the original graph. And there's an old theorem of Nesetrill that says if I'm looking at a connected graph, so if I'm looking at a connected graph, every locally injective endomorphism is an automorphism. So again, an endomorphism is just a homomorphism from the graph to itself. If it's locally injective, it must be an automorphism. So I don't have a map from G to its core, presuming that its core is a proper subgraph, that's locally injective. So there's a couple of immediate corollaries of this theorem. So if G is connected, then G is a core, if and only if all of its endomorphisms are locally injective. This is sort of the most straightforward way of stating this corollary. But we're actually going to use a slightly weird looking version of this corollary. What I'm going to do is I'm going to interpose an auxiliary graph H. So a connected graph G is a core if and only if there exists a graph H such that I have a homomorphism from G to H, and all of the homomorphisms from G to H are locally injective. And now we can see what the strategy is. So if I have a graph that's, say, uniquely colorable, I can check the unique coloring of that graph. That's a homomorphism to some complete graph. And if it's locally injective, then I win. My graph is a core. Of course, that doesn't actually work. So colorings are not the right setting to apply this corollary. The right setting is vector colorings. So if you remember back, as I said, if we were looking at one-walk regular graphs, specifically the graphs that I'm going to apply this to are distance regular and non-bipartite. They're going to be uniquely vector colorable. I'm going to show that they're uniquely vector colorable, the graphs we're interested in. And because they're uniquely vector colorable, and because the canonical vector coloring is injective, it immediately satisfies this local injectivity property, and I get a graph H for which all of the homomorphisms from G to H are locally injective. So which graph are we looking at? So what's the natural graph to define? So I'm going to define an infinite graph. The vertex set is going to be every vertex on the unit sphere in Rm. And my adjacency condition is going to be exactly this condition from our definition of strict vector coloring. And indeed, I could have defined strict vector coloring in this way. So now what can we show? It's the very last thing I'll write down. So our theorem, or part of two of our theorems are the following. So the Kneser graphs, K and K, which I introduced before, and their Q analogs. The Q Kneser graphs, so what's the Q Kneser graph? So for the Q Kneser graph, I'm looking at, so Q, K and K has vertex set the k-dimensional subspaces of the vector space GFQ to the n. So Q is some prime power. And the adjacency condition is that two subspaces meet are adjacent if they meet trivially. So if they meet in a zero subspace. So this is a theorem, and I don't blame you for not oohing and awing. This is, of course, well known. But our proof is kind of nice. So we get a new proof of this fact, and in particular, we get a proof of this fact where we don't have to look at the independent sets. So in particular, if you look at the standard proofs of these facts, they invoke the Erdős-Corrado theorem, which is a bit of a sledgehammer in terms of proving this result. And we've kind of found a way around that, which is nice. And I'll just say one last thing. So we also have a new result, a new class of graphs that are cores. We were able to apply the exact same technique to find a class of graphs in the Hamming scheme, the binary Hamming scheme, that are cores. So that's another example of some distance regular graphs. And those graphs weren't previously known to be cores. So that's all I'll say. Thank you for your attention.